Log on, tune in, find out. Another good idea from Cambridge.
Thank you very much.
Okay. I want to thank the organizers for giving me the opportunity to speak here. I thought it would be a good idea to explain how someone working in, at least on the analytics side of automorphic forms and higher rank groups thinks about it, and to mention some results which have at least been useful for Michael and Pierre and myself in our joint work. They came to me with some problems about Eisenstein series on higher rank groups. I won't talk so much about E8 here. I'll try and stick to SLN. And I hope to talk about a little bit about how you take Fourier expansions, how you look at the Laplacian, and a little bit more about some other questions in spectral theory related to the Langlands program. It's only an hour talk. I won't be able to get very deep with any of these, but at least I plan to at least present a picture of it. I think to even start about it, at least to explain this analytic perspective, I need to talk about SL2. So I'll begin talking for the beginning part of the talk about just about the theory of classical holomorphic modular forms. So I'll start with the complex upper half plane. Later there'll be a group identified with this, but for now I'll just think in terms of hyperbolic geometry. Well, why not have the group now? So SL2R acts on the upper half plane, acts transitively, and the stabilizer of the point I is the orthogonal group. Of course, this is the usual fractional linear transformation action. So the classical holomorphic modular forms are holomorphic functions with certain transformation properties and also a growth condition. Let me just try and emphasize each of these points, because one of the main points of this lecture is to explain how these notions get enlarged to other groups. So this is really the key property. This is transformation law. Of course, I haven't explained what it transforms under quite yet. Okay, so k is an integer, it's a weight, and this is for matrices in a discrete subgroup. There's a very rich arithmetic theory if you look at congruent subgroups of SL2Z, but I'll just stick to SL2Z. A congruent subgroup is a subgroup of SL2Z, which, as its name suggests, is defined by congruence conditions on each of its entries. One of the nice beauties of higher rank groups is that this definition doesn't even really matter for SLNZ. Anything which is a finite index subgroup is a congruence group. So for that reason, I'm going to slough over this point, but I don't mean to imply there's nothing to it. It's just that for time considerations, I'll ignore that. So this is really the feature property. So k is the weight. Now, once one has this property here, at least for SL2Z, it's clearly periodic in Z, because you can take an upper triangular matrix like this. So then you get a Fourier expansion because it's periodic. Should I put this higher? I can reach it. I guess I should use it. So this is called the Q expansion. So just from thinking about y as a fixed variable and then x as a periodic variable, the expansion looks like this. There's some coefficients. There's the phase. And this is what Michael and Pierre are interested in a lot of questions. And then beyond that, well, because it's holomorphic, in principle, there'd be a function of y here. I could write c on y. But because this is holomorphic, there's only there's only one possible solution in this case because it's holomorphic, and that forces it to look like this. So you could write this as e to the 2 pi I n z for short. So I just want to emphasize that this comes from a differential equation. Yeah, there's much, and this is just the start of the theory. There's a lot of things I haven't mentioned here, like Heck operators, and I really won't have a chance to say much about them today. I now like to turn to a different type of object on the upper half plane, which is not holomorphic, and which already manifests itself in a lot of papers in physics going back, well, certainly to the mid-90s. I don't know what the exact origin is. And these are non-holomorphic forms. They are also called Moss forms. These also come up in arithmetic. Maybe a rough way to make a distinction is that algebraic number theorists tend to look more at these objects. Analytic number theorists maybe are the ones more concerned with these objects at times. It depends on the question. These came up in some classical problems also, even though they don't look like it at first. So these are, okay, let me just emphasize they're non-holomorphic, but they do satisfy a differential equation. They're eigenfunctions of the Laplacian. Okay, so this plays the role of holomorphicity here. It's interesting that this is a second order operator, whereas the holomorphic condition here is really a first order operator. You can say it is d bar of f is 0. But there's some symmetry here, which is, there's actually a way you could unify this together where the Laplacian sort of factors into a different equation where that comes out of it. So it's really the same phenomena. It just looks there like a one variable, or sorry, a first order operator. One of the key differences in this theory is that whereas here, if you have k equal to 0, you only get the constant function. Here you can take k to be 0, so you have a simpler transformation law, but the objects are far more complicated. I can't write down any of them for you. Well, I can write down Eisenstein series, but the ones that are not Eisenstein series, and which are the more interesting ones, are so transcendental that there's not a single feature of them which for at least for SL2Z can be written down explicitly. Their existence was only known by Selberg when he invented the trace formula, which he did for that purpose, just to show they exist by counting them. So if you string theorists see these coming up in vibrant context, this will be very interesting to us who study these, because we don't have any concrete way that we can write them down. Okay, so here's a transformation law. So it's simply a weight 0 transformation law. And when one looks at the Laplace condition, you can still try and do a Fourier expansion. And so the Fourier expansion, I can write it here. There'll be some constants, and there'll be this phase. As a function of y, though, there are actually two different solutions that can come up. One of them blows up at infinity. By the way, I should have said here something about the growth condition. So the growth condition is that all these coefficients for n negative vanish. And that's a boundedness as z goes to infinity. And there's a notion of cusp form. Cusp forms actually decay as z goes to infinity. So that means that C0 is 0. So it'll be a similar story here. But here, actually, n will go over all the integers. And there are two different solutions. One of them blows up at infinity. That's the I Bessel function. The other shrinks, which is a K Bessel function. So I'll look at that solution here. That's, in a sense, you can view this as part of the definition of the growth condition if you want. So this is to satisfy a growth condition. So we just say that this, one way you could say it is this has to have polynomial growth. And that enforces that one gets a Bessel function here. And then there's also a notion of cusp form. And that's, again, that C0 is 0. So the cusp forms are very mysterious. So the only thing I can really write down for you, other than the constant function, which is not why you want to listen to this, is the non-holomorphic Eisenstein series. So the original Eisenstein series, the holomorphic ones look a lot like this. There's no y on top, and instead of an absolute value, it's just the quantity to a power, an integral power. Those are holomorphic modular forms. In this case, all the definitions are satisfied. You can write an explicit Fourier expansion. Maybe I should write that down just because it's so useful. So this term is C0. And then there are other terms. And then you can write an explicit formula for Cn in terms of divisor sums. So this exact expression is something that has a lot of meaning to Michael and Pierre, for example. They can count windings of branes. Pardon? Yeah, I should have put a phase there too. Yeah. Good idea. So they have independent of this calculation. Oh yeah, sorry. This is the completed Riemann zeta function. Thanks. So I hope later in the talk to show you what the general formula is, at least for the constant term for higher rank groups. There are no more ingredients to it beyond what's here. It's just more complicated combinatorics. They have predictions from a completely different point of view than this calculation involves, that are more geometric, about wrapping of branes, for example, that explain many of the key features of this formula. For example, its asymptotics, the exact arithmetic nature of these coefficients. And they have questions like this for higher rank groups. And we've been looking at a lot of these questions. And so far, all the predictions that we can test have worked out exactly with this type of calculation. So that's, of course, good. I don't know what you would do to me if it didn't. Okay, so these are arithmetically interesting. A lot of analytic number theorists are interested in questions where you average divisor sums and want to know about the magnitude of them. And these are things that can be naturally approached through these Eisenstein series.
Sorry. For the ignorant amongst us,
Of course, yeah.
Divisor sum?
Oh, okay. A divisor sum. It's open here. So you sum over all the divisors of an integer, positive divisors, and you take the divisor to that power. So for example, if a is 0, it's counting the number of divisors.
Yeah, okay.
These are, I mean, it looks simple, but it's very subtle. If you had a computer which could rapidly compute these quantities, you'd be able to factor integers and you could break RSA. So these are not the easiest things to study in the world. I mean, they're not the hardest things either sometimes. But. So Michael and Pierre have interpretations of these. Okay, so that's SL2. I think I should mention just one more idea about SL2. I could also mention that you can think of this, but I wrote this incorrectly here, by the way. All right, I'll put that back. This is just a normalization for the relatively prime terms. This has an interpretation of the average of the imaginary part of z to the s power. And what you'd like to do is sum over the entire group gamma, and then you'd have a gamma invariant object. But this is already invariant under certain things, namely the upper triangular elements. So gamma infinity are things of the form 1n, 0, 1. I'm only writing things here for SL2z. Okay, so maybe I'll put this here. I want to mention an important concept just to indicate how this will generalize to groups. I didn't even start with a group. I started with the symmetric space, the upper half plane, which of course is a quotient of SL2R by SO2 just because of the group action statement I made here. So this is a notion due to Gelfand and Graev, and it's really a crucial idea. So what they do, the point of view they have is instead of looking at these as functions on symmetric spaces, you can think of this really, this Moss form, as a function on a group, G, which is right invariant under, well, K is maybe not the best letter. I'll put K theta just to emphasize it's an SO2. So if you right multiply by anything in the compact group, in this case, you get an invariant function. This is saying that this is just decoding the group action. And one can do a similar thing here. Now there's too many Ks, but it won't be, you won't have the same invariance, but you get a character. So you get, all right, chi. So originally, Gelfand was studying the question of homogeneous flows. He was looking at, I think, the unipotent flow and the geodesic flow on different Lie groups. And he looked at this flow in the quotient of G mod gamma, and then somehow it led to this. And this is now, for many purposes, the most common point of view. So we look at the space L2, a G mod gamma. And we want to know, essentially, what are the functions on this space. After all, if you get rid of the condition here about the growth condition, if you ignore that and you ignore the Laplace condition, this is just some invariant function. So the point of view they have, of course, noticing that this property of multiplying on the right by K is crucial here, is they ask, how does G act on this space, and how does the space decompose under that action? So the right regular representation is simply the map, let's call it rho, which sends a function f to its evaluation at a point which is translated on the right. That's a group action. This is the space is a representation of a G under that action. And you could try and decompose it. Try and decompose it into irreducible representations. And these are automorphic representations. So an automorphic representation is a representation of a Lie group which occurs in L2 of that group mod a discrete subgroup. So I don't need this to state the definitions, but I think this is a very important point of view. I mean, for example, one of the calculations we were working on, we had an explicit Eisenstein series on a higher rank group. We wanted to show that many of its Fourier coefficients were 0. In principle, we could try and do a terribly long computation to do it. But then we learned we could use representation theory to immediately see many of the coefficients had to vanish for reasons that came purely from some considerations of semi-simple Lie groups. So let's see, maybe I leave this up. Talk about SL3 here. So here's higher rank. So I'm now writing the relevant symmetric space for SLN. It is not hyperbolic space. Hyperbolic space is rank 1. This is rank n minus 1. Okay, so here this is G, and this is K. And you can think of this as positive definite symmetric matrices that have determinant 1. The way you see that is if you take a matrix G here, and you map it to G times G transpose. And it's possible to write down the differential operators here. Okay, so here gamma, of course, could be a discrete subgroup like FL and Z. Let me write down the differential operators. Over here, there's only one differential operator that came up. That was the Laplacian. As I mentioned, in the holomorphic case, it's really also just the Laplacian. It's not the Laplacian necessarily on the symmetric space. It's technically the Casimir on G, which is, I mean, the only reason it's not, there's a different name for it is because there's the signature of the Casimir is a little different than that of the Laplacian. Looking for where I put the eraser, here it is. But in the higher rank case, there's many more differential operators. Not just the Laplacian, not just polynomials in the Laplacian. There's really a different algebra structure to it. So let me mention that. And I'm not interested in just any differential operator. The ones that are relevant, and which are exactly the powers of the Laplacian here, are bi-invariant differential operators. There's a ring, bi-invariant really, I don't need to say bi. So what that means is that if I take a function, so this will be acting in G. I mean, basically it means it commutes with this action, but I'll just write it down as a formula. So when I'm thinking of this function G here as being in the quotient. That's why I didn't act on the right, I acted on the left. And I don't know why I wrote that. That's stupid. That's better. So this differential operator acts in a way which commutes with the left translation of the group. So for example, if you have an eigenfunction and you translate it by something in the discrete group, gamma, which is acting on the left, you get back to the same object. Okay, so this algebra is a polynomial ring in n-1 generators. Now one of these generators is a Laplacian. The other ones are not. And I can actually write down an explicit formula. Let me write that in terms of coordinates on this space up here. So if I think of this matrix Y, which is the positive definite symmetric matrix, I can just label the coordinates of its entries. I'll put a half for the off-diagonal ones. And then let's let this symbol denote a matrix of partial derivatives. So here's the differential operator. So I'll take Y inverse, and then, times this differential operator, and then I'll take it to a power. So in other words, I multiply it again and again. And this is a differential operator. Once I take the trace, I can have it act on functions. And here k will go from 2 to n. And these are the generators. So the one for k equals 2 is Laplacian. Not at all obvious from how this is written out. It's a calculation in differential geometry, but it is the same Laplacian up here, the hyperbolic Laplacian when n is 2. This formula, in a way, I mean, this is tractable. You can write it down. It's not easy to work with. But in a way, it's why the representation theory is so important. In terms of the representation theory, when you have an operator like this, it has to act on an automorphic representation by a scalar. That's simply a consequence of Schur's lemma. So it's an automatic condition on an automorphic representation. If you don't know about automorphic representations, you may try and write down spectral theory and try and diagonalize the space under these operators. This does it for you. Okay, so now I'm now trying to generalize the definition, so I guess I should now state what it is. So it's an eigenfunction of the full ring. And well, just like before, what was missing? It's automorphic. But just by the way, I've set it up. It's automorphic under this discrete group gamma. So here, gamma, for example, is SLNZ. But there has to be something else. I had a growth condition before. So let me now state the growth condition. Naively, it's very similar. It's a statement of polynomial growth. And I can say it as follows, that if I take f of g, this will be bounded by, let me say big O, of the sum of the squares of the entries of the matrix G to some power. That's a way to state the growth condition. It's maybe not the most intuitive way of it. It's probably the simplest way to make the statement. And again, for n equals 2, this does coincide with the growth condition that I stated before. Okay, so now let's come to the Fourier expansions. Oh, I'm sorry. I want to say cuspidality first, just to make it simpler. Okay, so the notion of cuspidality is more difficult here. It's not simply the vanishing of a single coefficient. The statement is the following. So a certain set of integrals has to vanish identically. So there are these certain unipotent subgroups that come up. They look like this. So you have the identity matrix in these two blocks on the diagonal, and you have arbitrary entries up here. This is a unipotent subgroup of SLN. And the function is invariant on the left by gamma, so of course I mod out by gamma so I don't repeat the same thing over again. And this integral should be 0. So when n is 2, this is just the identity matrix except for an entry above the diagonal. That corresponds to the x variable in the theory of SL2, and then that's the statement that the the 0th Fourier coefficient vanishes. So the big challenge here, and again, it's even harder, of course, for SLN than it is for SL2, is to write down cusp forms. We understand in principle the entire set of automorphic forms from knowledge of the cusp forms. I say in principle because there are a lot of details which we have not worked out, but certainly if there were no cusp forms, there wouldn't be much of anything else. And again, it's not obvious that there are cusp forms. Maybe I won't go into that now, but it's now known that they exist, but again, by very indirect counting arguments. We don't even have the full trace formula available quite yet to do that in all cases, but there are some tricks that can be applied to that. The reason that's hard is because these quotients are not compact. So spectral theory works very well in producing eigenfunctions for compact surfaces. Here, there's a continuous spectrum as well as a discrete spectrum. The continuous spectrum comes from Eisenstein series, and there have to be bounds to show that the Eisenstein series aren't beefy enough to sort of eat up all that the Weyl law would allow for a surface. Okay, so hopefully later in the talk I'll write down Eisenstein series and I'll explain the constant term formula. What I'd like to do now is explain how the Fourier coefficients can be written out, the Fourier series expansion can be written out for an automorphic form. And I'll state it just for cusp forms. It's certainly more complicated for the non-cuspidal forms, but the idea is the same. And the 28 minutes, I don't want to go too much into that. So I think what I'd like to do is just to begin explaining it for SL3, just to give the idea. So this is an expansion that was due to Piatetsky, Shapiro, and Shalaika. They did this independently in the 70s. I'm not sure which was first. And I think it's worthwhile to go through the mechanics of at least the idea for SL3 because it's something which we use a lot to understand relation of different Fourier modes. Okay, so let's start with this cusp form. And the first thing I want to do is I want to write a Fourier series for it, but see, the upper triangular matrices, which is the group that's sort of naturally coming up here, is not abelian. And you can't write Fourier expansions on non-abelian groups without throwing away a lot of material. So what I'll do is I'll look at a certain subgroup. And I'll put this G here for a second. So this is an abelian subgroup. And since I'm invariant under SL3Z, this function is periodic separately in Z and Y. And it's smooth. I mean, it better be smooth. It satisfies the Laplace differential equation. That's tacitly, I mean, no one would make such a statement otherwise. So you could write this as a Fourier expansion, and then the theory of Fourier expansions in two variables says the following. There's two variables, m and n. You go over the integers. And then you integrate over 0, 1 each variable. Oh wait, so this is a physics talk officially, so I'll do it this way. I think I prefer doing this way because that way I don't forget to put it later. I think I don't know. Okay, so we like to leave the entries blank if they're 0. Okay. I don't know if I had this notation before, but it's useful. So when I write E of U, it simply has a 2 pi I factored out of it. Now, being a mathematician, I might forget and write it again, but I didn't. So just have dz dy1. So this is just the theory of Fourier expansion. What I wrote is sort of silly here. Sorry. Let me now set this to 0. If I set this to 0, this is the correct statement. This is a theory of Fourier series in one variable. Namely, if you write the function at 0 as a sum of each of the Fourier coefficients. Okay. Now, if f were just any function which is periodic under this group, that's about all I could say. But f has a lot of extra invariants. This is just a small part of the group. I'll go over here. So a key idea is that they look at invariance under a matrix like this. They can embed SL2Z into SL3Z. I'm just sticking up in the top right corner. And by the way, even this is not using the full invariance of the group. To get the full invariance of SL3Z, you need to use these entries on the bottom. So then you can compute this Fourier coefficient. So for free, I can put this matrix in here now because it's invariant. Okay, let me just do something a little sneaky. I can put the inverse here just as well. Now I can change variables. I could send zy goes to az plus by, cz plus dy. There's no change in measure when I do that because this has determinant 1. So if I do that and combine with this, what I'm left with is the same type of integral. So this inverse here will undo this change of variables here. So I'll have So I've just passed this matrix through, and when I did that, I altered what z and y were. That's why I changed the variables first, so that it would look nice. And then on this side, now I've got minus m az plus by minus n cz plus dy, dz dy. And this can be simplified as minus ma plus ncz minus mb plus nd y. So I've got now almost the same type of integral I had when I started. I've now seen that there's a relation between these different Fourier coefficients. What's the relation exactly? So we related this. So let me give this a name. Let me call it Vmn of G. So now the relation I've shown over there is that V ma plus nc, comma mb plus nd, abcd inverse g is equal to this. Now this action here, of course, this is just the action of mn by SL2z, but the other way around, from the left. So when you're taking a Fourier coefficient of automorphic form, the discrete group actually permutes the characters around. Of course, at the same time, you have to translate the argument of the function. So these things fall naturally into orbits. So it's very natural to look at SL2Z orbits. Now, since the whole reason I'm here is because these are also BPS orbits in a lot of cases. Now these orbits, what I've written here is a very general phenomenon. I just have a paper on the archive with Siddhartha Sahi where we talk about this for higher rank groups, and it's written in a way that's supposed to be useful to Michael and Pierre for some other calculations. That's certainly what motivated it. Michael and Pierre had studied these same actions, again, from a different point of view, and they come up together in these Eisenstein calculations also. So what are the orbits in this case? They're indexed by non-negative integers. And here's a representative for each orbit. So another way to say it, and this is essentially just the Euclidean algorithm to take the GCD of two integers. If you have Vmn, parentheses there, it's SL2Z equivalent to something where the first coordinate is 0 and the second one is the GCD. So that means that this sum can be reorganized. So this formula I have there, I can put k on the outside. And now I'll write, there'll be some gammas here. I'll write out exactly what they are in a second. And now on the inside here, I could look at V0k, and then I could write gamma 1g. And then what's V0k? That's a much simpler type of integral because it only depends on one of the variables here. So it's constant in z. Now, so what gamma are here? It's the same ones that came up with the Eisenstein series before. Well, there's a small plus or minus factor, but let me just slough over that for the time being. Okay, what's the point of that? Okay, well, this is organized in a different way, but now there's a special property that this coefficient has which the other ones don't have. If I go back to this translation formula here, one particular point is that if I take this matrix to be upper triangular, in other words, just if C is 0, if C is 0, I don't fix this coefficient because the n part will still get, the b won't be 0 necessarily, and so if it's something non-zero here, that will carry over here. M times b will be non-zero. But if the first guy is 0, like it is here, by just a direct consequence of that calculation, this is now periodic in this variable. And now I can do another Fourier expansion. I have this position of the matrix left. This is exactly now one variable Fourier expansion. And so I can do a Fourier expansion in this variable here, in x. That's, again, a one variable thing. So what that will reduce to is that if I leave the k and the gamma on the outside, I can write a third sum for v0k. So now let's call it, well, you guys call it n hat. I'll call it m. I already used m. L as L. And now I'll have the integral here. Now I'm integrating over the full group of unit upper triangular matrices. This is the maximal unipotent subgroup. And this is essentially an arbitrary character of this group that is trivial on the integers. So this is now an integral over a pretty big subgroup. It's over the unit cube. And this is called a Whittaker integral. Now, Whittaker, of course, never studied this integral. He studied some analogs of some confluent differential equations, and he has generalizations of the Bessel functions. Bessel functions came up before for SL2. There are Moss forms of other weights. One can write a theory for that. Whittaker functions appear there instead of Bessel functions. And because of that analogy, these functions are called Whittaker functions. There are even p-adic Whittaker functions, which Whittaker certainly didn't study. But this is, I just want to explain the name. And there's a theory of Whittaker functions that because there are differential equations here, and because these are so constrained, because I'm integrating over a large subgroup here, if I translated here by saying in that subgroup, it would transform by a character. So this is a function which can't do very much, and because of the differential equation and the growth condition, it's exactly a constant times a fixed special function, which, of course, is called a Whittaker function also. For n equals 2, this is the logic that gave the exponential for the holomorphic forms and gave the Bessel function for the non-holomorphic forms. And this uses theory of partial differential equations. The cleanest way to state it is that I know is actually in terms of representation theory, but there's a one-dimensionality statement that comes up that it has to be exactly this function. That would not be true if I integrated over a smaller group. For example, if I integrated over the trivial group, I couldn't possibly make such a statement. So there's a balance that comes up of trying to get to as big a group as possible, but which is still flexible enough to write something. And here for SLN, Piatetsky, Shapiro, and Shalaika both found that this argument generalizes to larger matrices. You sort of keep working one column at a time to the left. And they have an inductive formula that involves a sum over a discrete group and over integers times 6 special functions. So in general, we would like to get our hands on these coefficients because we could test some statements that came from string theory about the asymptotics of these functions. So I'd like to now, in the last 12, 13 minutes or so, I want to mention something more about spectral theory and low eigenvalues. This was something that was curious to me that it came up. And there are still some unsolved questions about automorphic forms. This was the first time I saw something about Arthur's conjectures coming up from string theory. There's been a lot of work with the Langlands program, more of the type of the geometric Langlands program. But there's another area which I think was really the original thrust that has to do with arithmetic about lifting between automorphic forms on these groups and these quotients here. So there's actually for this I should write down the Eisenstein series. So there's a notion of Borel-Eisenstein series. And I probably want to go a little more quickly than I meant to. This is a maximal, well, I don't want to, maybe I shouldn't talk about Zariski closure. This is a minimal parabolic. So for SLN, it's just everything that's upper triangular. That would be what this is. And let's say we take a character of it, not necessarily a unitary character, you could call it a quasi-character. In this case, the character depends only on what's on the diagonal. And so we could take simply the character which sends us to. I'm going to have some funny normalization here, just so things work out nicely. So I take each of the diagonal entries to a different power of my choosing, but I've normalized it here with some shift by an integer. This is rho, for those who know about it. So the Borel-Eisenstein series, E lambda, a G, so sorry, y lambda, you can write this in Lie theory notation as a to the lambda plus rho, or a is the torus part of the parabolic. So this character is trivial on the integral points from the general theory. And this is how the Eisenstein series is defined. Okay, I hope at the end to say a little more about that. So what's interesting is that this function here, the function, so I have to explain this notation a little more. What this means is you take gamma g, and then there is a Iwasawa decomposition, so you can write this as NAK, or so B is NA. N is the uniponent radical of the parabolic, so that's the unit upper triangular matrices, this object. A is the diagonal matrices in this context, it's the maximal torus. And K is a maximal compact subgroup, so it's again SON. So these are all things that came up earlier. In a way, this plays the role of X when you look at SL2, and this plays the role of Y. So you take this, and then you apply this character. So I write this to lambda plus rho. I'm just applying the character to A. So this is actually an eigenfunction of the ring of differential operators. And as such, as long as you can prove convergence, which is a certain range in which it's valid, namely in that range, this sum converges and it gives an eigenfunction of all these operators, and that's the minimal parabolic Eisenstein series. All the other Eisenstein series that have come up in string theory are special values of this Eisenstein series. The fact that this is an eigenfunction is useful because it's hard to write down these operators. We know this from soft principles why it's an eigenfunction. But then this lambda gives us a good way to parameterize the eigenvalues of these operators. So what one could say in general is if you have a cusp form and you want to talk about what its eigenvalues look like, you could match it up with an Eisenstein series which has the same eigenvalues. So this lambda technically here, it lives in the dual of A, the complex points of the dual. So to each cusp form F, can associate lambda sub f in the dual such that f and this character up here, which I wrote like this, the same eigenvalues. Under any invariant differential operator. This looks a little awkward, but at least it's a way I can state something. So there's a conjecture which dominates a lot of the analytic part of the subject. It goes by the name of Ramanujan-Selberg. The Ramanujan part is more arithmetic. It's directly related to the famous Ramanujan conjecture about the size of tau, his function from the coefficients of his modular form. And the Selberg part has to do with a conjecture for SL2 about eigenfunctions of Laplacian. Okay, so for the Moss forms I had before, so for these automorphic forms I had before, which I assume to be right invariant under K, the real part of lambda is 0. So lambda is purely imaginary. That means this character here, other than the row shift, takes modulus 1. So this is a subtle statement. If you just wrote this character above naively with powers S1, S2, it would be harder to arrive at this statement. The row comes up quite naturally in there. So for example, the Laplace eigenvalue here's a formula for it. N cubed minus n over 24 minus the sum of the squares of these lambdas from above over 2. So in particular, this would be at least n cubed minus n over 24 by the conjecture. The relevance to string theory is that there are equations which Michael and Pierre have been trying to solve, along with Jorge Russo. And they are differential equations. Sometimes they're homogeneous, sometimes they're inhomogeneous, but they have prescribed eigenvalues, and those eigenvalues are sometimes below this range. They can't, there could be cusform solutions in principle to their equations. It would be very hard to see because they only know usually the gross asymptotics towards infinity, and cusforms decay rapidly at infinity. So it would be almost invisible to their detector in the way of these equations. So it'd be nice to know that they had the exact solutions to their equations, that there were no cusforms there. This is a tradition in analytic number theory. There are, of course, a lot of questions like if you want to show it, maybe the most famous one is to show a number is the sum of 4 squares. You can write out a statement about, you take the theta function to the 4th power, you get a modular form of weight 2 for a certain group, and you'd like to equate that with an Eisenstein series whose coefficients are positive. That would, by combining the formulas, show that you can write each positive integer as a sum of 4 squares. There are no cusform solutions there, so it's an amazing exact formula. So in this situation, I want to mention a result that implies this. So it goes back a while, and I didn't realize it would be useful to this. If you look at SLNZ itself, this conjecture is supposed to work for congruence groups also, and it's much deeper. But for SLNZ itself, the Laplace eigenvalue is at least n cubed minus n over 24. In fact, plus a little bit more, plus I think like 0.08 n. So there is some separation, and we can use this to have at least proofs, or in other cases, very convincing arguments that there are no cusform solutions to their equations. To do that, we need to use Arthur's conjectures because we work on E8. And it's not, this statement is only for SLNZ, but the Langland's conjectures relate sometimes automorphic forms on some groups to others. And when you have bounds on one group, you can apply them to other groups. So I want to end now just by explaining just a little tiny facet of the grand scheme of the Langlands conjectures, but one which is extremely deep. And this is Langland's symmetric power lifting. Just want to give the idea of how this fits together, so at least you've heard of it. I'll state it just for SL2, but there are versions for all sorts of different groups. So if you have a Moss form, there was this parameter nu I had before in the Bessel function. No one stopped me, but I didn't write what it is. It's the Laplace eigenvalue. You write it as a quarter minus nu squared. So that nu is essentially the lambda I have now is nu minus nu. So what this conjecture states is that nu is an imaginary number. And the Laplace eigenvalue, according to Selberg, should be at least a quarter. We don't know how to prove that. But what Langland says is that you should be able to lift this. So it should lift to an automorphic form. On SLN. And there, so let me call that capital F. And this vector lambda f I had before, so this is lambda little f, it looks like this, but it's been magnified a lot. So it's n minus 1 nu, n minus 3 nu, and so forth. It goes down by 2 each time. We only can do this up to n equals 4 so far, but this conjecture we can go beyond that. Now what happens every time is that these numbers are getting much larger. There is a statement that comes from elementary representation theory. I shouldn't say elementary. It's actually relatively deep, but it's called the trivial bound. So it's actually not at all elementary. But it has been known for a while, and it doesn't use any particular arithmetic feature. I guess that's what I should have stated. So since I'm on tape, I have to apologize to Jacquet and Shalika because it is a deep result. But somehow it's called the trivial bound. There are results like this for many other types of groups. And the idea is that we know sometimes a little bit about representation theory that can go a long way. And the bound is the following, is that the real part of any of these lambda j's on SLN is never more than a half. You can improve on this, but what's important is that that's a fixed value. So what would happen here? If you had something which violated this conjecture, if nu had a real part, I lift it to SL a billion, and then the real part is a billion times larger. Eventually, I keep making that number bigger, it's going to get bigger than a half. And so the conclusion is, this implies, among many other things, that the real part of nu equals 0 if arbitrarily large lifts exist. Now, in closing, Langland's conjecture is also that any automorphic form at any group lifts to SLN. So if you want to make a statement about some type of statement about all automorphic forms, SLN is not a bad place to look. And so the strategy we have, essentially in arguing that there are no cusp-form solutions to some of these equations, is we lift from E8 to SL248 or whatever. And we check that it's more complicated than this, but there's still this type of feature that if the Laplace eigenvalue is below where we want it to be, it still corresponds to something that is contradicted by this statement. Okay, well, my time is up. Obviously, I could go on for years talking about this and still not get very far. But now it's probably a better time to stop then.
Any questions? Just a quick one. You mentioned E8, so throughout this you spoke about SL groups.
Yeah.
If you do things like the exceptional groups, then are there special things that happen for the exceptional groups that do that for SL?
Well, yeah, so there are sometimes special bad things that happen, and sometimes special good things. Here's a very bad thing that happens, and this has been terrible for us. This argument here fails very badly. I use the fact there is this orbit statement up on top. It's far worse than this. There are representatives of different types. And there are many types that come up. Of course, that's good from the point of view of string theory, because otherwise some of your statements would be false, I guess. But everything matches up. There are these more complicated half and quarter and eighth BPS orbits that correspond to what I call here character variety orbits, right? That's what we call them. And it's much more intricate to try and do this. We can't write an expansion of this type down using just sort of Abelian analysis. On the other hand, there are some special things that do come up, is that there are some exotic representations that do appear, representations of the real group that do appear, that at least in some cases we looked at, force those coefficients to vanish. So in that sense, it can be simpler. It can be simpler than this, but usually it's much, much worse. Okay, thanks.
Thanks very much.